Okay. So this is a lecture that if you've taken a class with me before, you may have seen before. We're going to talk about randomized rounding. Okay, so this will be an algorithm class. The usual recap. What have we done? We've done some linear of expectation with some kind of warm-up applications. We introduced hash functions with the heavy hitters. We also used Markov's inequality. We did linear probing as sort of our case example of a hardcore hash table. We did that randomized contraction min cut algorithm. Hopefully that was fun. And last time it was a little more mathematical. We analyzed these random graphs. It was supposed to be an example of concentration phenomena. Right? It was really about how once the sum gets large enough, it becomes extremely concentrated around the average. Okay, and then kind of shows up in this creative sideways kind of way in the case of random graphs. Okay, so today's going to be about approximation algorithms. Um, so and a standard technique for it called randomized rounding that's useful for many approximation algorithms. And the three examples I've chosen, one is maxsat. I'll introduce in more detail in a moment. Another is set cover. And then if time permits, there's covering integer programs, which is sort of a generalization of set cover. But okay, so this is really a story of kind of two things, right? So we're going to try to bridge, as you well know, some problems we can solve exactly in polynomial time, other problems we can't. So what do we do for the problems that maybe we can't? Sorry to disappoint. Um, so yeah, there are some problems, in fact, that we can't solve. And so what do we do? Well, it's not necessarily NP hard to approximate them, right? It doesn't imply that you can solve SAT problems if you get a certain approximation. Uh, and that's going to be paralleled by kind of interpolating between two things, continuous optimization, which will be represented by linear programs, and discrete optimization, which is sort of the thing we're after, that NP hard solution that we're after. And we're going to connect those two with randomization. Okay, so sort of the basic starting object. Okay, looks a little uh, mathy, but they're very simple. So these are called integer programs. They're almost like the simplest possible kind of math program, except the variables are restricted to be integers. Okay, so uh, maybe here you have some variables x, and they're just required to be integers. Okay, maybe it could be 0, 1 for like yes or no. And you have some objective. You want to minimize the sum or maximize the sum, whatever. Okay. And then you have a bunch of constraints represented by linear inequalities or equalities. So like, oh, x1 plus x2 has to equal 0, x3 plus x4 has to be at most 1, or whatever, right? So from a mathematical point of view, this is like the simplest possible thing because you're only dealing with linear objectives and linear constraints. And in the math world, nothing's easier than a linear function. Okay. Okay, but all of these are rapidly NP hard because you can easily take whatever's your favorite problem, independent set, whatever you want, and figure out how to write it down as an integer program. And we'll do that in a moment for our applications. Okay. All right. Linear programs are the exact same thing, except the variables are not constrained to be integers. Okay, so instead of saying it has to be 0 or 1, you could say any value between 0 and 1. Okay, so that's the only difference, is that now the input or the variables are allowed to take on continuous values. Okay, otherwise exact same. Okay, an example of linear program that probably you've all seen before is the max flow problem, right? So there you're trying to like send as much water as you can from S to T, through some pipes, right? And so you can represent the flow of water in each pipe as a value, 1 unit of flow, 2 units of flow. And the pipes have some capacity. They can only handle 1 unit of flow, 2 units of flow. Okay. And you also have constraints like, oh, the flow that goes in is equal to the flow that goes out, right? So I sum up all the water going in, has to be equal to the sum of the water going out. So that's just a linear equation. Okay, so max flow, everything can be expressed linearly. All right, good. The important part, whereas linear integer programs were NP hard, linear programs are actually polynomial time solvable or weakly polynomial time solvable, which means you take into account the bit complexity of the input. Okay. And at some level, like people are very comfortable solving linear programs in practice. So this goes back to 1947 was a simplex algorithm uh, by Danzig. Does anybody know the famous Danzig story? Okay, so when he was kind of close to your age as a graduate student, uh, and maybe like you, he slept in and missed most of class, and he came in late. And the teacher had left some homework problems written on the blackboard, and he wrote them down and took them home and thought really hard and came back and turned it in. And the teacher was like, "What the hell? Those were open problems." And one of the open problems was, I don't know if the word algorithm was necessarily in the parlance, but coming up with a methodical way to solve linear programs. Okay. And it turns out that, during World War II, he had kind of worked in operations research for the army, had been working on some special cases. But so this algorithm that he solved for homework, um, for no credit at all, uh, didn't even get to self-grade it. Uh, that became this famous simplex algorithm, and it's not actually a polynomial time algorithm. You can come up with examples where it take forever, but it's very practical. Okay. The first theoretically polynomial time algorithm doesn't show up for 32 years or something. And that was like a major open problem at the time, especially since the simplex was working so well in practice, but they couldn't prove it worked. And this is called the ellipsoid algorithm. This is by a Russian named Kachyan. And he was using a high dimensional geometry theorem called John's ellipsoid theorem. And it's really well, maybe I won't sketch it out, but it's sort of a high dimensional geometry heavy kind of thing. Okay. And then, but this was, I think this was like New York Times kind of front page kind of stuff. But it wasn't very practical. It was mathematically correct and nice, and it's still useful in theory a lot, but it wasn't considered as practical. Uh, this was followed up a few years later by Carmarker, I think it was at Berkeley, was what was called an interior point program. And this looks a little bit more like your typical convex optimization program that's going to use kind of convex penalties for when you start to approach the constraints and things like this. And otherwise, do something like Newton's method, some kind of gradient descent type thing to solve it. Okay, but then there's a lot of work to show that Newton's method, and if you set up the barrier functions just right, will take strong, weakly polynomial time. Okay, and since then, there's actually been a lot more progress. Okay, so what's the difference? So on the left we have discrete optimization, which is kind of our original interest. We actually want to solve something that's modeled in the real world, some yes and no type of questions. And on the right we have kind of continuous optimization, integer programs versus linear programs. The difference is that integer programs are NP hard, and linear programs can be solved. So at some level, we are trying to get at integer programs or special cases of integer programs, and we have sort of computational access to linear programs. Okay, I'm omitting, there's a whole industry of kind of more heuristic-based integer program solvers. Okay, good. So we're going to be studying LP-based approximations. So what does that mean? You take whatever problem you're working on, independent set or whatever it is, and the first step is to model it as an integer program. Usually this is not too tricky, but we'll go carefully through our first example. And then we take that integer program and we just relax it to a linear program. So same math. I'm just saying now it can be fractional values. You can take 0.3, okay? And then we'll feed it into some kind of black box LP solver, okay? And that'll give us some kind of fractional solution, some optimal solution. And then this is at some level a good solution for slightly the wrong problem, a relaxation where you're allowed to cheat by taking fractional values. But at some level, it's very good. It'll still satisfy all the constraints. It'll have a very good objective. It'll only have a better objective than the true discrete op because the fractional values just give more flexibility. Okay. So now we just want to take that fractional solution and convert it into a good integral solution. Okay. So we're gonna use kind of the fact that we can solve LPs as a very powerful black box. And then we just have to figure out how to kind of interpret the fractional solutions with regards to our original discrete interest. Okay. And in fact, one thing we're often going to do is, this fractional solution X will have some objective value. It's worth 10 points or something, right? And at that point, 10 is actually at least as good as the optimum solution. So if your goal is to say minimize, and you're able to convert X into some Z that's worth 20 points, you're also within a factor 2 of the optimum solution. Because X, which was worth 10, is at least the optimum if you're trying to minimize. So 20 is within a factor of 2 of something that's at least as good as opt. Yeah, so the fact that you can also on the spot, verify your approximation factor is also very valuable. Okay, so that's the paradigm we'll explore. It's useful for a lot of problems, but here's just kind of some warm-up ones or introductory ones. Okay, so the first one we'll do is max sat. Okay, and so sat we've already done. We did it in the first lecture, and you probably killed it to death in your previous algorithms course. Previously, we had done the 7/8 approximation, and we even de-randomized it and all this kind of stuff. Now, the one key difference today is that we're going to allow any number of variables in each clause. And it can be mixed. The first clause can have 2 variables, the next clause can have 100, the next clause can have square root n. Okay, so it's just going to be mixed. This is kind of the fully general one. Whereas before, it was always exactly 3 variables per clause. Okay, so let's say that ksat means there's exactly k for each clause, and then maxsat means there could be any number in any clauses. Okay, and imagine our oblivious algorithm. We just flip coins for each one, right? We did specifically 3 sat, but I think it won't be too hard to extrapolate what you get for other values of k. So for example, if k is equal to 1, what would our algorithm have gotten? Just flipping coins and there's 1 variable per clause. That seems a little crazy, but it would just be half. It's not a great algorithm, right? You should be able to get opt. Okay, what about for 2? 3/4. Also not a great algorithm. You can get opt. Okay, 3 we did together. That's 7/8. 4 would be 15/16. This would be, right? And in general, you're going to get like 1 minus 1 over 2 to the k. But if we applied our algorithm to just max that in general, what's the best approximation factor we can guarantee? 1/2. Yeah, you're getting killed by the k equals 1, which isn't even that hard. Okay, so at some level, we don't have at the moment, a great approximation algorithm for max out. 1/2 is pretty lame. Okay. All right. So we're going to take this kind of approach. We're going to write down the integer program, get a little practice with that, relax it, and then figure out what to deal with it. Somewhere randomization will enter the picture. Actually. Okay. So I left some stuff blank so that if this is your first time, you can try filling it in. So for example, okay, so let's say that there's n variables and m clauses. I know they sound the same. So m as in mom clauses. And so what do we need? So I've created for every variable x1, x2, x3, a variable y1, y2, y3. And for every clause c1, c2, c3, a variable z1, z2, z3. Okay. And so what we really need is some kind of objective. I guess I already filled in max for you, and some kind of constraints. And maybe also some interpretation for the variables. If I said zi, that's corresponding to clause I to 1, how should I think of that? If I set variable j to 1, xj to 1, how should I interpret that? All right, anyone want to fill in any of the boxes? Yeah. Okay, max sum of z, what does that mean? Okay, which means I think implicitly you're setting, Okay, so what we're going to do for the clause variables, and I'm going to think of setting it to be 1 if I'm satisfying that clause and 0 otherwise. And then my objective will be summing up those ZIs because I want to satisfy as many clauses as possible. Okay. All right, so now we just have variables that we want to interpret, and we need to come up with some kind of constraints, right? Because right now, unconstrained, you just set all the z's to be 1, and that would seem awfully crude. So how should we model constraints? Okay, so this will be 1 if it's true, 0 if it's false. Okay, so now how do we model? Okay, so that's easy to interpret, right? Because like Boolean variables. Now, how do I come up with clauses? Yeah. Yeah, okay, so like for this example clause here, okay, I should only be able to set z1 to be 1 if somehow these variables indicate something true, right? So if x1 is true, then yj will give me 1 point. And if x2 is false, then 1 minus y2 will give me 1 point, right? Because 1 minus 0. And if x3 is true, then y3 will give me 1 point. And I need at least 1 point out of those 3. So I can set this to be greater than equal to z1. Okay, so it's saying if you want to set z1 to be true, you have to get at least 1 point from one of these 3. You have to set either y1 to be true, y2 to be 0, or y3 to be true, and that will exactly what you're looking for. Okay, so that will be us modeling the constraints. Okay, it looks messy to write a sum, but I think it's intuitive. Okay, any questions? All right, so to turn this into a linear program, we're not going to do anything clever. We're just going to say, instead of saying 0 or 1, you can choose any value between 0 and 1. Okay, but otherwise it kind of has the same semantic meaning. 0 kind of still means false, 1 kind of means true. What does half mean? I don't know, but. All right, so good, good. So we wrote down an integer program that captures the original maxsat exactly. But it's empty hard because it's just maxsat. We get the LP, that's actually solvable. Okay, and one thing to point out here, we're trying to do max, so bigger is better. Is that the optimum value of our LP is always at least the optimum value of our integer program, because anything that's valid here is valid there. Okay, good. All right, so let's say that you put it through this kind of pipeline, you put it through the LP solver, and now you have some fractional solution, you really y and z. But at the end of the day, what you want to do is you want to output an assignment of variables, right? So you put it through your LP solver and you get some fractional vector y. Variable 1 is 0.2 true or something. So, and what we want to do is we want to now convert that into actual assignments. Okay. All right. Any ideas? Yeah. Sure. Okay. So one option is that, like, if I had x1, like we can do kind of like deterministic rounding. So I can write like true if y1 is greater than or equal to like 0.5. That seems natural. False. Um, Otherwise, okay. Which is also the same as y1 less than 0.5. Yeah. Still satisfy what? Okay, so when we write the linear program, I still carry the constraints. So I have the same constraints here. And the linear program, I mean solver, will satisfy these constraints. So we'll have to check. Yeah, that's absolutely true. That's absolutely true. Yeah, yeah. So we need to we can't like if we didn't have to worry about constraints, we just make everything big or something and make all the z's one and yeah. So we have to be yeah, we have to be mindful of the original problem in general. Surrounding is non-trivial. Good. Okay. So this is a very natural idea, right? This is like just rounding in the usual sense of the word. If it's at least half, I round up, and if it's less than half, I round down. Yeah. Okay. Any other ideas? Yeah. Mhm. Yeah. So maybe the left hand, maybe the earlier slide's better as the example. If these are two of these are true, right? Then you have 2 points on on this side. But z1 is still constrained to be at most one, so you can still only get 1 point for this constraint. And that's sort of what you want, right? Because in constraint satisfaction, even if two of these are true, all that matters is that C1 is true. So that's totally, yeah, we have greater than equal, so that's totally fine. Does that answer the question? Yeah, some level it's a non-issue. It's totally fine if it's two on the right. Yeah. There may be other problems where we want things to be exacting, but for this problem, it's okay if the left is bigger than the right. Okay. Now, for example, one thing to be like wary of is if I have some constraint like x1 or x2, with things that are, like deterministic rounding, if each of these was 0.33, or let me write 1/3. If each of these was 1/3, thanks, Corvid. Okay, it equals 1/3, right? Then you would round all of them to false. Okay, but in the LP, you might have set this clause to be true because they got you one total point, right? So I think we can actually mess around with this kind of basic template and suddenly get ourselves into trouble. Yeah. Sure. Okay, so that's another idea. We can maybe try randomized rounding instead. So instead of doing deterministic rounding, where the catch is like, okay, I could start thinking of bad examples like this, where you're always like rounding down or in some bad direction. Randomized rounding, I can't quite, force you one direction or another so easily. So that's what we're going to try. Maybe this is a little too small. Okay. So at some level, the question is, how do I interpret y1 equals zero point 0.5. What does it mean to be zero point 0.5 true, zero point 0.5 false? Okay. And what we're going to do is we're going to interpret that as meaning half the time is true and half the time it's false. Okay, so any fractional value you can try to interpret as a probability. Yeah. And see how far that takes you. So that's what we're going to do. So if yj was set to be 0.1, then 1/10 of the time it's going to be set to be true. 9/10 of the time it's going to set to be false. Okay. All right. So that's the rounding we're going to pursue, randomized rounding. Okay? And it's going to be independent. That's also important. Okay. So anything down here? I guess not. Okay. So okay, good. So what I want to show is that every clause is satisfied with probably 1 minus 1 over e zi. Okay, so every clause I is satisfied with probability 1 minus 1 over e zi. Okay. All right. Does what's down here? Okay. Does anyone want to get us started? So let's say that the clause, just for concreteness, I'm looking at a clause that looks like x1. Let me do it right here. Suppose I have a clause that looks like c1 is equal to x1, or not x2, or x3. Just want to figure out what are the odds of c1 being satisfied. Yeah. Yeah. So you have some values y1, you have some values y2 and y3, right? So you want to figure out what are the odds that they all kind of come out tails, come out the wrong way. Or, okay, like before, it's actually easier to analyze the probability it's not satisfied because then you have this kind of, oh, only one outcome is possible. Okay, so let's do that. Probability that CI is not satisfied. Okay, so what's the probability that CI is not satisfied? Yeah. Yeah, so maybe if I take like the product, I mean, this notation is makes it more complicated than it looks, but I take the product of, every variable xj that appears positively in CI, so I'll kind of abuse notation and write xj and CI, right? I want it to come up heads. In the bad cases, it comes up tails. So I think that'll be 1 minus yj, okay? And then also the product with all the variables that appear negatively in the clause, so not xj. I want that to come up tails. So the bad cases, it comes up heads. That happens with probability yj. Okay, that would be the general expression. But I'm just multiplying things together, just like we used to do 1/2, 1/2, 1/2. All right. Now this is sort of messy to deal with analytically, right? At some level, basically everything we do, like sums are easy, right? Like linear programs, everything's summing. Like the sums of yi's, we understand, right? Because the sums of yi's need to be at most zi or something, or at least zi. Like they have some semantic interpretation. But the direct kind of probabilistic analysis gives you this kind of product, and it's a little hard to relate to the LP. Okay. So how can we deal with that? Sorry? It's true. You could take the logarithm, and then you're going to get a sum of log of 1 minus yj's and stuff like that. But then you have another problem of how do I interpret logs of the variables? Okay, we're going to use the only thing we ever use in this class. Okay, this time I wrote it out, drew it ahead of time. So 1 plus x is less than or equal to e to the x. Okay, and what this trick does, okay, it's a little painful because like you have to write in smaller font because it's in the exponent, but now it's going to be a sum. Okay, so you're going to get a sum of e to the negative summing over xj and ci yj. I mean 1 minus yj, right? And I put the negative sign in front of the sum. Okay, and then for the other product, okay, yj doesn't look like 1 plus x, but 1 plus yj minus 1 does, or something. So, okay, it's a little more convenient to write this way. Like this. Okay. You might have more naturally thought yj minus 1, and I just put a minus sign and I swap that. Okay, but we're using the same inequality, you just had this 1 plus 1 minus 1 quietly inserted. Okay. And let me make this a little bit cleaner and see if it rings any bells. Negative, let's just put the whole thing in parentheses. Okay, so I'm summing over all the variables that appear positively, yj, and I'm summing over all the variables that appear negatively, 1 minus yj. Okay, so this is great. So you started off with this mess of a product, and the font got a little small because you're in the corner, but otherwise this sum is somewhat more friendly. Okay, so now can we interpret this sum? Yeah. Okay, this appears in our in our LP, right? That sum is greater than or equal to that variable, which if we do this correctly, should get you something like e to the negative zi. I do that right? It's greater than or equal, but there's a negative sign. Say less than or equal. Yeah. Yes. Yes. What's an inequality between friends? Okay. Although that won't help you on the homework. Okay. Uh, all right. So is that okay? So we've taken this mess to begin with. I mean, it's kind of simple probabilistic event, but it's hard to interpret this. And then we do this nonsense, and then we get to here. Okay. Good. So now, did I set this up correctly? Okay. There's a cleaned up version. All right. So now that we need to deal with this term. Yeah. Ah, okay. Can we use that in reverse? So that would get you something like, okay, so e to the x is less than equal to 1 plus x squared for small enough x. Or actually, it'll be x squared over 2 for x less than equal to 0. So this is going to be less than equal to 1 minus zi plus zi squared over 2. Sorry. X is negative zi. Okay. Now what? The problem is you have this quadratic term. Well, like for example, you could do 1 minus zi over 2, because zi is at most 1, right? Okay. So if you did this, then what we have shown is that the probability that Ci is satisfied, which is 1 minus this thing, is at least Zi over 2 with that inequality, right? That means that what's the expected total number of clauses that would satisfy if that was the case? So the expected number of clauses that are satisfied, huh? Sorry? Okay, so by linear expectation, we could sum over all these clauses Ci. You get the probability that Ci is satisfied. You'll get some sum over Ci, Zi over 2. And then what's the sum of Zi over 2? It'll be at least, what do we know about the sum of Zi? Sorry? It is less than M. What else do we know about Zi? It's a solution to the LP, so it gets you at least opt, but opt over 2. Okay, so we have a 1/2 approximation, which is what we already had from the coin tossing. So we haven't won at all. So actually, this inequality down here is actually not going to be strong enough for us. Yeah. I can raise both sides of, sorry? Uh, sure. Uh, e to the minus x is less than equal to 1 over 1 plus x. But isn't this also very close to 1 minus x plus x squared over 2? I mean, yeah, it is. Or, really order x squared. Okay, let me give you uh, another suggestion. Yeah. Uh, is it less than 1 over e? It's at least 1. No, it's at least 1 over e. It's at most 1. Okay, I have a picture. Oh, I erased part of it though. F of x is equal to e to the minus x. Okay, so f of x is equal to e to the minus x is a convex function, right? And so I can look at, this function's being plotted. It has some value at 0. It has some value at 1. And it has some value at zi. And I know that the place of the curve is bounded above by, where that straight line would be. Okay? So e to the minus zi, this place, this part on the red line, what is this called? A chord, maybe? Secant? A secant. Okay. Well, we have most, 1 minus zi times e to the 0 plus zi times e to the 1. It's like your usual kind of convex analysis inequality. Okay? So let's try plugging that in. Um, 1 minus zi e to the 0. I'll write e to the 0, but that's of course equal to 1. Plus zi e to the 1, which is e. I'm just putting the 0 and 1 there for the convex part. Okay, so what does this become? All right, so this is something like 1 plus e minus 1 zi. Oh, I made a mistake. So this should be minus 1. Right? Yeah. Yeah. So this should be minus 1. So let me write it this way. 1 minus 1 over e ci. Okay, sorry about that. So we're plugging, it's f of x is equal to e to the negative x. So we should be plugging zi equal to 1 into that function. You get e to the minus 1. Okay. All right. So new inequality, threw it out at you. Here's a cleaned up version. Okay. But now we get to our claim that each clause will be satisfied is probably 1 minus 1 over e. So we actually use a slightly better inequality. And we got up from 1/2 to 1 minus 1 over e. We use kind of convexity. Okay, good. Okay, so now the claim is that the expected number of clauses overall, when you round, will be 1 minus 1 over e times opt. We just did this kind of together going through the 1/2 example, so I'll be quick. You can do linear of expectation, use sum over all the clauses, the probability of the clause ci being satisfied, and that's, we just showed 1 minus 1 over e times zi over all ci. And now the key point is that the sum of zi's, because they solved the LP, will be at least opt. Okay, so it's very important that the sum of zi's have meaning. That's related to our original problem of interest. All right, make sense? So yeah, as often the case, the algorithm is very simple, and then there's probably a little more analysis than you're used to, but you'll get used to it. Okay. Okay, good. All right, good. So we can get 1 minus 1 over e for max that. Okay, and now the next question is can we get better? Okay, so to this end, okay. All right, so before we showed that each clause, is satisfied with probability 1 minus 1 over e zi, right? And that was, no matter how many variables, you get 1 minus 1 over e. But let's look at a couple simple examples. What if ci had one variable? And we did this randomized rounding. What is the probability that ci would be satisfied if it had one variable? It'll be whatever that variable yj, and zi is going to be equal to yj, right? It's going to be as big as possible. So you're going to get exactly zi. You're not going to have to give up a 1 minus 1 over e if it were one variable, which is also good. That's kind of, you're hoping you do well one variable. That should be pretty simple. Okay, so that's good. All right. What if you had two variables? So if we had two variables and we start doing something like before, the probability of CI is not satisfied. Okay. And let's say for the just for an example, it is x1 or x2. If it was a not, it would be easy to adjust the following calculations, right? You get, well, they have to both be tails. 1 minus y1 times 1 minus y2. Okay. Now, before we use that e to the minus e to the x trick to deal with it, but for 2, there's actually another one that's sometimes useful. So again, the usual situation is that it's messy to deal with products. I would like to kind of pull out a sum. We can use AMGM. Should be, okay, we can use something like AMGM. Okay. Uh, so this product will, I guess, be the sum of these things put together. Yeah, okay, so we'll get 2 minus y1 minus y2 over 2 squared. Okay, good. Uh, which you can also think of as 1 minus y1 plus y2 over 2 squared. Okay. All right, how can we deal with this? Sorry? Oh, can you just do 1 minus z right away? Well, we could see. That's not what I had in mind, but uh, wait, well, so one sec. Z will be at most this, so I'll be okay, right? Something like this. Oh, is this easier maybe? Well, let's just keep going. Let's see what happens. Otherwise, I have the other version approach. Oh, this is what I did in notes? Okay, great. All right, 1 minus zi plus zi squared over 4. Did I do that correctly? Where do the notes go from here? Oh, there's an issue in the notes. Ah, okay. This is better than what I had, which is even though I had it. Okay. So zi is at most 1. Yeah, so I can replace zi squared with zi over 4. So we get 1 minus 3/4 zi. Oh, excellent. Okay, this is better what I had in mind. Okay, although apparently I did have it in mind. Okay, so 1 minus 3/4 zi, we reciprocate, I mean, 1 minus this thing, we get 3/4 of zi instead of 1 minus 1 over e. Maybe I should have mentioned that 1 minus 1 over e is something like 0.68-ish. Yeah, okay. All right, so the point is, for one variable, you get all of zi. For two variables, you get slightly better. You get 3/4. Okay, was it 0.68 something? Oh, okay, it's the other one. Okay. Okay, good. Okay, forget that one. All right, so with that in mind, okay, so what did we show before? The oblivious LP does better for larger values of k. Okay, and our LP-based approach, in general, it gets 1 minus 1 over e, although for specific 2 and 1, you get slightly better. Okay, you get all of them when the clause has 1, and you get 3/4 when the clause has 2. Okay. Now, what's kind of interesting about this is that the average of 1/2 in zi is like 3/4. Okay. So it's 3/4 zi. And of course, 3/4 and 3/4, the average is at least 3/4 ZI. Okay. And here you need to do the math, but the average of 7/8 and 1 minus 1 over E is also at least 3/4. Don't know exactly what it is, but I promise it's at least 3/4. Okay. And then the rest are even bigger. Okay. So we have this funny kind of thing going on where, okay, so our goal is to deal with any K, right? But for any particular K, I have pretty good strategies, right? For K equals 1, K equals 2, the LP does really well. And for everything afterwards, a random rounding does really well. I mean, the original oblivious rounding does really well, right? And at some level, we have kind of two strategies that on average will get you 3/4. Okay. Our goal is to try to do better than 1 minus 1 over E. Our goal is to try to get 3/4. Okay. And we sort of have two strategies that can kind of separately, in some funky way, kind of finagle 3/4. So how can we try to combine these two ideas? Any ideas? How can I try to get sort of the best of both worlds and get a complete 3/4 approximation for max set? Does the question make sense, or why it's interesting make sense? We can get 1 minus 1 over A for any K. Yeah, for any particular K, we have some combination of strategies that does better. I wish I could somehow, in some slick way, sort of combine both the algorithms together. Yeah, can you take both and take the better one? But how do you justify that? Or will be another algorithm? How can I combine two algorithms? At some level, you can only do one thing, right? Huh? Okay. Some people have seen this lecture. Okay. So what you can do is you can flip a coin. Okay. If heads, you'll do that oblivious algorithm. If tails, you'll take the LP based approach. Why is that? So that's very nice, right? Because it actually lets you kind of do both algorithms, even though, of course, you can only do one. You're just doing each one half the time. Yeah. Well, you can, but you can only output one of those assignments. But why would one of them be good? The max is probably in what sense do you okay, when you say the max is probably higher than the average? Yeah, I just want to be a little careful when we say average because this is some kind of like intermixed thing, right? So some clauses do better under one and some clauses do better under the other. Okay, so let's if you flip a coin and you do this, now the claim is that every clause will be satisfied with probability 3/4. Okay. And now this just comes from the table. Let's say the clause has 10 variables, right? Half the time you do the random oblivious approach and you get 1 minus 1 over 2 to the 10 chance of satisfying it. The other time you do the LP based approach and you get 1 minus 1 over E times the Z variable. Okay, so every clause ultimately is satisfied with probably at least 3/4 ZI, no matter the K. Now you plug that in, you do the same math as before, and you're now satisfying 3/4 of all the clauses on average. Okay. Now that you have this, now you can go back and realize that the max of the two will do better, right? Because the average of the two strategies get you 3/4, but first you have to establish that the average of choosing one random strategy or the other gets you 3/4. Okay, I went a little quick. I didn't do the calculations on the whiteboard. I can, but is there any questions? Does that make sense? Yeah, so if we flip a coin, yeah. Uh, well, okay, yeah. So okay, so okay. If 7/8 is so easy, why don't I take my one clauses and add variables, make them bigger and stuff, right? Okay, so and why stop there? Given my 3 sat, why don't I make it into a 4 sat? So what goes wrong? Yeah, so you have to be careful. Like, let's say that I naively wanted to take a one variable clause and turn it into three, and I had two dummy variables. Right, that was a three set, right? And then you randomly flip coins, and one of your dummy variables make it come true. But that's not helping you with the original formula. Okay, so really, what's going on? Often we do. You might have seen in a prior algorithms class, things like, oh, if k sats np hard, k plus one sats np hard, and you can figure out something where you add a variable or take away a variable with some gadgets, for k bigger than three, right? You might have done this exercise, looking at some of you, and and but that we're just also only preserving like exact stuff, right? Exactly solvability of the formula. If you went through those, you might find that it doesn't preserve like the quantitative approximation, right? You're not necessarily, when you change one formula to another, kind of the fraction of clauses being satisfied starts to change. They're not approximation preserving. Okay, so that's what we have to be careful about when we start doing these gadgets and stuff, you know, in this world of approximation algorithms. Now your gadgets also have to kind of preserve the quantities in a non-cheating way. Make sense? Yeah. Okay, good question. Yeah. Well, you're gonna do at least as well. Uh, I think you cannot guarantee anything. These are worst case bounds. Good question. Maybe one question is there better than 3/4 approximation for max sat? Oh, there might be, right? Because there might be things using like semi-definite programming or something. There might be, but not within this algorithm. I mean, I think this algorithm, this analysis is tight. Okay. Other questions? Okay, then let's do one more example. This time we'll do the set cover problem. Okay, so hopefully you've seen set cover before. So your input consists of a bunch of points and a bunch of sets. Okay, and you want to select the minimum number of sets so you cover all the points. Right, so you're like a telephone company and you have to place cell phone towers to cover all the users, things like this. Okay, and it's empty hard. Okay, and at least I'm prepared to show you a reduction from sat. So you start with a sat instance, you're going to turn it into a set cover instance, and you want to show that, if you had some black box to solve minimum set cover, you'll be able to solve the original sat formula. Does anyone remember how to do this? So I give you a sat formula, and you want to turn to a set cover instance. Do any of you feel like you've vaguely seen this in your distant past and just forgot? But you always seen something like it before? So maybe this will be familiar once. Okay. Anyone want to guess? There's no harm trying. We're not going to shame you. Just try to imagine what would be the harm of trying. Something catastrophic happens because of a wrong reduction. Okay, well, you have to make sets. You have to make, oh, yeah. Okay, so just to map like things you take to require and to things you take and requirements to requirements. So we think that sets should correspond to assignments, like setting x1 to be true might correspond to a set x2 to be. And then the requirements are coming from the clauses. So you have elements for every clause and something like this. So taking the x1 set will satisfy that first clause. Yeah. Okay. But what's the one issue with this configuration? Well, you're still incentivized to pick the minimum number amount. You could pick neither x1 nor x1 bar, which you're supposed to pick at least one. And there's another issue. You can also pick both x1 and x1 bar. All right, so how do I enforce this last bit? Yeah. Okay, so we're going to have now elements for every variable to kind of satisfy this exactly one constraint. Say, okay, sort of that element corresponding to the first variable can only be satisfied by taking the set for x1 to be true or the set for x1 to be false. So you have to take at least one. And the question is, can you get away with taking just one of each? Okay, so you can show that f is satisfiable if and only if there's a set cover of size n, which means you're taking exactly one from this pair, one from this pair, one from every pair. Okay, all right, so you've probably seen this before. Good. All right, that was fun. Let's write an integer program. Okay. So, so what might be an objective? What would be the variables? What would the variables correspond to with respect to kind of the semantics of the problem? Like I should have a variable for every blank set. So I have a variable for every set because that's what I'm choosing. Okay. So maybe the natural way to interpret it is if I take the set, I'll set it to be 1. If I don't, I'll set it to be 0. Okay. All right. So what about the objective? What about the requirements? What about the objective? Yeah. Yeah, I want to take the minimum number of sets. So I'll minimize the sum of xj's. Good. What are my requirements? So here we actually don't have any variables for the points. Before we did have a variable for every clause, but we're actually going to do without a variable for the points. So for every, so what does the problem require? For every point we need, yeah. You do like the matrix multiplication. Okay, for just one point, like without, yeah, give me a little more simple terms. So in the sense that cover a given point, the sum of the. Yeah, let me just rephrase a little bit. For each point, the sum of the sets covering it needs to be at least 1. Okay. So for every point that's represented by some index I and m, if I sum over the sets where I is in Sj, xj needs to be at least 1. Okay, so every point needs to have at least one set. Every point, the sum of those indicator variables of the sets containing it needs to be at least 1. Okay, good. Okay, so turn this into an LP. I just put this between 0 and 1. Now you're allowed to take half a set. Good. We're doing fine. And then just like before, we had an integer program that really didn't do anything but encode it, in fancy math terms. So it's still NP hard. It's basically the same problem. We'll convert it into an LP just by relaxing it. Now you can actually solve this thing. Okay. So, right, it's polynomial time solvable. Okay, good. So now our exercise is, you plug this into your LP solver, and it's going to give you these fractional values for all the set. 0.3 of this set, 0.2 of that set, 1 over e of that set. And now you want to actually convert it into a family of discrete sets that you're taking. It needs to be a set cover. It needs to cover all the points. All right, any ideas? Yeah. Okay, we can do the same thing as last time. For every set Sj, if it has value 0.3, I'll take it with probability 0.3. Otherwise, I'll leave it out. Yeah, that's the same thing we did last time. So we're going to just interpret the LP values as probabilities directly. Okay, simple enough. Good. All right, let's start analyzing this. Maybe we can start with, okay, so I'm letting like F denote the family of sets we actually take. So size of F is the number. Yeah. Oh, we haven't yet. Yeah. So we'll need to analyze both the size of this thing, and then we also need to consider whether it's actually a set cover. That's absolutely right. Good. So just hold the thought. Okay. So but we'll start with, because it's the easier calculation, the expected size of our set cover. Okay, the number of sets we actually take. All right. So what would this be? It'll be the sum of the xi's by, our usual like linearity of expectation would be appearing here. We have indicator variables for every set. And the first set is taken was probably x1, the second variable is taken was probably x2, and so forth. And the sum of xj's will give you the opt of your LP solution, right? That was your objective. So that's good. So you're actually getting an optimum size solution. Okay. All right. So then the next thing, is it here? Oops. Okay. Oh, it's not what I wanted. Oh well, that's okay. Sorry about that. I goofed out a little. Let's fix a point I. Okay. And here I would have made it more rhetorical, but I blew it. So let's look at the expected number of sets that cover that point I, right? And we would do some linear of expectation that I didn't write out explicitly, but ultimately I would sum over all the sets that contain that point, the probability of taking that set. The probability of taking that set is xj. So it'll be at least 1. Okay? So that's also good. You're at least expecting to cover every point. Okay? But that's not really what we're interested in. What are we really interested in for a particular point I? That tells us on average you get 1 set. Yeah. Yeah, you're really interested in the probability that it's covered, right? And it turns out to be easier to analyze directly the probability that it's not covered. Okay. So what might I do here? How can I bound the probability that the point is not covered? So what has to happen for it not to be covered? Yeah, all the sets that contain it, I have to also flip tails. So we'll take the product of all j containing the point 1 minus xj. Yeah. Okay, yeah. If you start using AMGM with more than 2 variables, then you're going to start getting like cubes and fourths, and it becomes less useful, I think. But like right here, I mean, so you can have like AMGM was like 20 terms, 30 terms, but then you're looking at like the 30th root or something, right? Because the geometric mean. And by then, I think you're so far removed from anything that you can interpret, that it's going to be hard to pull out a bound from it. I think that's why 2 was useful and 3 wasn't. Huh? That's my sense. And I think the big thing is just like you're dealing with a third root, and it's like, okay, this sucks. Okay. All right. Okay. So we've done the same thing many times here. I have this mess of a product. It's hard to interpret. I know how to deal with sums. How can I convert it to sums? No, we're not going to take the logarithm. We'll use the only thing we know besides that one AMGM moment. E to the negative sum over all the sets containing that point, xj. Okay. And this is, sorry? E to the minus 1, because the sum of xj's is at least 1. Okay. Before that was like a zi or something. Now it's just 1. Okay. So yeah, so that's the cleaned up version. Okay, good. Um, all right. So that means that 1 over E, so that means that the probability that F covers I, we've shown is at least 1 minus 1 over E. Okay. Okay. So we've shown that F covers each point with constant probability. So maybe I can just like, I try this once, it doesn't work, I'll try again, keep trying until it turns out to be a set cover or something, right? All right, what's the issue? Yeah. Uh, yeah, okay, well, okay, just because F will cover any particular point with constant probability doesn't guarantee that it'll ever cover all the points with any probability, right? Maybe there's even, maybe it's impossible or something. So okay, so that's the basic issue. We have not actually shown that F is a set cover with constant or any useful, even polynomially small would be fine because we could repeat a polynomial many times, right? So we haven't actually shown something that works, right? So now the next question for you all is how can I tweak my algorithm to guarantee that it actually returns a set cover? So this gets back to the original question. Does this rounding actually give a set cover? And our initial rounding does not. So how can I make an adjustment? Yeah. Okay, so there are two approaches, and that's the approach I don't have slides for, but let me describe. So at some level, if you do this once, you should expect to pay opt, and you should cover 1 minus 1 over e fraction of the points on average. So most of the points get thrown out, and you paid opt. And then you do it again. You don't even have to resolve the LP. You can even re-round the same set. And then of the remaining points, each of them are still getting covered with probability 1 minus 1 over e. So most of them get thrown out and a little bit left. So each time you're expecting to throw out a constant amount, right? And once you do a logarithmic number of times, kind of similar to our quick sort high probability or something, your expectation is so low. You expect to have 0.000001 elements remaining. So you definitely have less than 1 with good probability. And you need about logarithmically many rounds to keep kind of pumping this. Because I'll give you a login approximation. That will work, but that's not the slides. So anyone have a second idea? Okay, so something much more involved. While we're rounding, keep track. What does keep track mean? Okay. Yeah, can you do some kind of adaptive rounding then maybe? Yeah. Well, I don't know. I mean, I can't rule it out, but I certainly have something simpler in mind. It's not clear. Like, let's say x1 you get unlucky or something, and well, I don't know. Maybe you resolve the LP, throwing away x1, but you don't quite know how much damage you've done. It seems hard to figure out how to make that useful. I can't rule it out, but and yeah, I'm looking at what I have in mind is a relatively simple idea, kind of simple, like repeating. Yeah. Oh, okay. Yeah, that doesn't seem. Yeah, I just have no idea how to analyze. So the idea was like, oh, maybe 1 point at a time. I'll try to pick one set that covers it in proportion to the x's or something, and then somehow keep moving on, keep moving on. Yeah, I'm not sure how to analyze that. Yeah. Yeah. So the other approach that I'm prepared for is to just scale up the x's first. So the x's were too weak, right? So the sum of x's got you like -1, which only got you, e to the -1 odds. But if I scale that up, then I can drive that probability down. So instead of rounding with probability xj, I'll round with probability 100 times xj or 1,000,000 times xj or something times xj, which makes it more likely for me to take any particular set. So on one hand, I'm paying more. My goal is to take as few sets as possible. I am paying more, but I am killing, dropping those probabilities down. Okay, so we'll figure out, what value of alpha I need to set to, and the actual trade-off. Okay, so just to repeat some calculations from before, if I was trying to figure out the expected value of size of f now, if I scaled up by alpha first, it would become alpha times opt, right? Because I scaled everything up by alpha, and our calculations will be the same. Think of alpha as 100. Everything's multiplied by 100. Okay, now when I look at the probability that f does not cover I, right? And if we kind of went through all those calculations again, 1 minus, now you're going to get alpha xj. You can assume alpha xj is less than 1, because if it was greater than or equal to 1, you're definitely covering that point, right? And then you're going to get your usual sum of alpha xj's, right? And here, instead of -1, you're going to get e to the negative alpha. Okay, so just scale up, everything goes through. Good. So now, what's the probability that f is not a set cover? Or, okay, our goal is to ultimately get a good bound for this, but I have some control over this. So I guess it's a two-part question. What should I set alpha to, and then how do I, show this is small? Okay, so if I set alpha to be like log n, say 2 log n, okay, then this will start becoming 1 over n squared. I had done 3, 1 over n cubed, etc. Right? Now, if I want to bound the probability that f is not a set cover, what should I do? We're going to use the union bound, right? So I'm worried about messing up any of the points, so I can take a union over all the points. So the union over all I will become a sum over all I. The probability that f does not cover I. Okay, now you're summing over all I, 1 over n squared. And then you multiply that by n, you get 1 over n. Okay. So now you give up a factor of log n in the cost. You're taking log n more sets on average because you multiplied all those probabilities up. But now with high probability, what you output will be a set cover. Yeah, so you can just ramp up the probabilities, and because it's sitting in the exponent, you can take the union bound. Okay, good. So that timing is perfect. Good. So that's your log n approximation. I'll only briefly mention what this was about. You can take set cover or really any problem, and instead of like saying, oh, you have some points that covered by some sets, you can start having like equations like, oh, if you take this variable, it adds 5 points to that score, 4 points to this score, all these different rows. And then each row has like some requirement. You need 10 points for this row, 12 points for this row. So it's just generalizing set cover. Set cover would be just only zeros and ones, because a set covers something or it doesn't, and then you have to take one for every. Okay. And the only point I would have wanted to make is that for this, we can do the same thing. We can, yeah? There is not. If you can do better than log n, then p is equal to np. Yeah. That kind of, yeah, that follows from PCP theorem and more approximation preserving reductions. Okay? Or kind of approximation mapping, because you have a constant factor hardness for 3 set, and that gets turned into log n hardness for set cover. So this was the best possible algorithm on this p equals np. So I'll only mention that you can do the same algorithm where you randomly round, okay? And rather than doing that kind of direct analysis we did, because you have these coefficients, it gets a little bit messier, you'll want to use the Chernoff bound and do some concentration. Okay, so If you kind of scale up, then you're expected on average to cover the rows. The average will be really high. You'll definitely cover the rows, so on and so forth. Okay, so all I'm saying is that there's some generalization where the analysis we did will get replaced by the Chernoff bound. Okay, and of course there's no time today to prove the Chernoff bound, so we'll do that another class. Okay, thank you.